Good afternoon, everybody. My name is Gaurav Chaudhary. I'm Assistant Professor in IT Department at Ajay Kumar Garg Engineering College, Ghaziabad. The topic for today is Bayesian learning, which is under the subject of machine learning. Now, before we begin to discuss about Bayesian learning, we will discuss what is Bayes theorem. So your Bayes theorem, it gives the posterior probability. It gives the method to calculate the posterior probability of the hypothesis given the data. So in Bayes theorem, we have your the posterior probability, which is calculated using the prior, which is given, and the likelihood of the data, and the evidence, which is the observation of data. So your Bayes theorem, we have the term pH given the observed data, which we are trying to calculate, and pH given the observed data, it is calculated in terms of P probability of data given the hypothesis into the probability of the hypothesis, which is the prior of the hypothesis, and divided by the probability of the data which is observed. So in Bayesian learning, what we do is we actually predict based on the all the combination of the hypothesis, instead of predicting just on the basis of one hypothesis. So when we predict the future instances based on all the hypothesis or the combination of the hypothesis instead of just one single best hypothesis, then it is called as your Bayesian learning. And when we select all the hypotheses, then all the hypotheses, they are weighted by their prior probabilities of the data given the hypothesis. So in this way, if we see this PHI given data is equal to alpha P D given HI into PHI, where alpha is 1 by D and it is also your evidence, 1 by evidence. So this is your constant term. So we can ignore this term while calculating the value of the posterior probability, which is PHI given the data. So in this way, the learning is reduced to the probabilistic inference, and because we are considering all the hypotheses for predicting our next instance, whatever we are trying to predict. So now we will see how we can approximate the best hypothesis among all the hypotheses which are present, which can be used for prediction and classification of data. So a very common approximation that is usually adopted in science is to make predictions based on your single most probable hypothesis, that is HI. We will select an HI that will maximize the term, that will maximize the posterior probability PHI given D. This is often called a maximum a posteriori or MAP hypothesis. So one thing is that we can calculate PHI by D using the Bayes theorem, but while calculating PHI given the data by using the Bayes theorem, we can also approximate the best hypothesis possible which can be used for predicting the future instances. and that is called as your H-map hypothesis or a maximum a posteriori hypothesis. So H-map is defined as argmax, where small h is element of capital H, and argmax of the term pH given the observed data. So if we can further elaborate this term, and this becomes, using the Bayes theorem, this becomes your argmax H element of capital H hypothesis set, and the product of probability of observed data given the hypothesis into the probability of the hypothesis, which is the prior, upon the probability of the observed data. And again we can ignore the denominator term, and this becomes your argmax H element of H, probability of observed data given the hypothesis, product with the probability of hypothesis, which is the prior of the hypothesis. So notice in the last term we dropped the term PD because it is a term which is a constant and it is independent of H. So this is the very first approximation. The next approximation is HML, which stands for hypothesis maximum likelihood hypothesis. This is your H subscript map. And next we are going to discuss is hypothesis HML. So we can further reduce this best possible hypothesis which we have calculated into HML. So how we can do that is that it is done on the basis that we have the term called probability of H, which is the prior over the space of hypothesis. So if that space of that prior over the space of hypothesis, if we assume that prior to be a uniform prior, that is that every hypothesis in H is equally probable, then in that case what happens is we can further reduce the best possible hypothesis, and the hypothesis which comes out of this process is known as your HML, and the argmax term gets reduced to only the probability of observed data given the hypothesis. So argmax pH d given H, and we have to select the best possible hypothesis, and that best possible hypothesis, if we have a uniform prior over the space of hypothesis, becomes your HML, which is your maximum likelihood hypothesis. So we started with our posterior probability. We started with the Bayes theorem, then we reduced that to find the best possible hypothesis. We reduced it to H-map, and then we further reduced it to HML. So this is these are the three variants or three ways in which we can use the best possible hypothesis. And when it comes to Bayesian learning, we will be seeing the concept of optimal Bayes classifier, because in that, as I have already said, we will be using the combination or all the possible hypotheses and multiplied their by weighted by their prior probabilities. So now coming to the topic of Bayes optimal classifier. Now so far we have considered that what is the question that what is the most probable hypothesis given the training data. So in that process we calculated the two variants, HMAP and HML. This will give us the most probable hypothesis. So if we want to predict a future instance, what we can do is we can simply use your HMAP or HML to predict the future instances based on this hypothesis which we have selected, which are the best possible hypothesis in their respective scenarios. But we can improve this further. Is that in the sense that we can find the most probable classification of new instance given the training data. So what is the most probable classification of new instance given the training data? As of now, till now, what we have found is the most probable hypothesis given the training data. Now the question is, what is the most probable classification of the new instance given the training data? So in that case, what to do? Whether to use HMAP or whether to use HML. So the thing is that we can actually do better in the sense that we can use combination of all the hypotheses weighted by their prior probabilities, and we will calculate the posterior probabilities of all the hypotheses, and that thing will be used to classify the new instance. How that will be used, we will see in the next few sentences. So now, suppose we have been given three hypotheses: H1, H2, and H3. Suppose that posterior probabilities of these hypotheses given the training data are 0.4, 0.3, and 0.3. So posterior probabilities, that means that given the data, what is the probability of the hypothesis of each and every hypothesis, and the probability of each and every hypothesis given the observed data is 0.4, 0.3, and 0.3. Thus H1 is the if we see the best possible hypothesis, then because your H1 is giving the probability to be 0.4, it is your map hypothesis. But in the Bayes optimal classifier, what we will do is we will use the combination of all the hypotheses to predict our new instance, predict the classification of our new instance. Now, taking all the hypotheses into account, the probability that X, your new instance, which is X, is positive is 0.4, whereas the probability that it is negative is 0.6, which is the sum of the posterior probabilities of hypothesis H2 and H3. So it is 0.3 plus 0.3, which comes out to be 0.6. So here the most probable classification becomes negative because we are using the combination of all the hypotheses in order to predict our new instance, classification of the new instance. So we can see that this classification is different from the classification generated by the map hypothesis, because the map hypothesis will say that it is a positive example, whereas your Bayes optimal classifier will say that it is a negative example. So it is different from the classification for the same example is different in the case of map hypothesis with respect to the classification given by the Bayes optimal classifier. Now we will see the equations which go into finding the posterior probability of each and every hypothesis, and then after finding the posterior probability of each and every hypothesis given the observed data, how we can use these posterior probabilities in our Bayes optimal classifier to predict the classification of the new instance of data. So if we see that any system that classifies new instance according to your equations 6.18, which we will be discussing just now, is called a Bayes optimal classifier. So how we are getting this equation, we will see. So first, what we have done is we have found your posterior probabilities, which is PHI given the observed data given the hypothesis, and probability of the hypothesis. Now, having calculated PHI given the observed data, these are the posterior probabilities of each and every hypothesis. So then we are going to use these hypotheses, these posterior probabilities as weights So we will be using these posterior probabilities as weights to calculate the classification of new instance given the hypothesis, each and every hypothesis. So it is a summation. So if you see now this second line, if you see the px given the observed data. So probability of a new instance x given the observed data d is summation over I, all the possible hypotheses, and product of x given the observed data and the hypothesis, and with product with probability of hypothesis given the observed data, which are the posterior probabilities which we calculated using the Bayes theorem. So this comes out to be summation over I over all the hypotheses, and the product of probability of new instance x given the hypothesis into probability of hypothesis given the observed data. So we can see here that we are classifying the new instance x based on the summation of all the hypotheses, and we are using the probability of classifying new instance x given the hypothesis, each and every hypothesis, which is weighted by the posterior probability of each and every hypothesis, which is the term phi/d. So you should be very clear here that we are using the posterior probability as weights for all the posterior probability of hypothesis as weights for selecting those hypotheses while predicting the new while predicting the classification for the new instance of data. So this equation is what we are using in our equation 6.18, and before we come to 6.18, we say that the probability of classification of a new example that can take any value vi for some set v, then the probability of vj given the observed data d, that the correct classification for the new instances vj is just p vj/d. So here the vj is the term capital X that we saw in this equation, px given the observed data. So your vj is the value of the new example, because your new example can take on any value. So that value, and that comes out to be similar to this equation, exactly similar to this equation, which is the summation of all the hypotheses and p probability product of probability of vj given the hypothesis weighted by the posterior probability of all the hypotheses, which is the term probability of hi given the observed data. So the optimal classification of the new instance is the value vj for which pvj/d is maximum. So if we take the argmax over the possible values of the new example, which is the vj are the possible values of the new example. So for that value of the new example for which this term comes out to be maximum, that will be the optimal classification for the new instance. So if we see in our example, we've taken this example, the set of possible classifications of the new instance v is, what are the possible values of set v? They are the positive classification or the negative classification. These are the two possible values of the new instance, new example for which we have to do classification. Then the classification is a binary classification, whether it is a positive example or whether it is a negative example. So if we use this equation, we will find that for the we have to calculate the posterior probabilities of all the hypotheses, and these values are given. And if we see that your now if we see this example, so we can see that the posterior probabilities are given. In the example, we don't have to calculate. They are given for reference. So for each and every hypothesis given the observed data, we can see that PH1 given observed data is 0.4, PH2 given observed data is 0.3, and PH3 given observed data is 0.3. And in the equation, then we will have to calculate for the values of the example. So values of the example can be positive and negative. So P negative given H1 is 0, P positive given H1 is 1, P negative given H2 is 1, and P positive given H2 is 0, P negative given H3 is 1, and P positive given H3 is 0. Therefore, if we take the summation, so summation we will take for once we will take for the positive values, and then we will take for the summation for the negative values of the new example. So if we take summation of the positive values, we will see that it comes out to be your P H1 D, it comes out to be 0.4, and your this for the negative values, the summation comes out to be the summation of the two hypotheses H2 and H3, which comes out to be 0.6. So if we take the argmax, the maximum value of the maximum values which can be maximum of the values which can be taken by the new example. So if we take the maximum of those values, so we will see that the maximum for the negative negative classification comes out to be 0.6, and maximum for the positive classification comes out to be 0.4. So based on this, the classification becomes a negative classification. So this is your this is actually your Bayesian learning, because here the learning is a probabilistic inference, because we are using the combination of all the hypotheses which are present, and we are weighting those hypotheses by their posterior probabilities. And in that sense, it becomes the learning. Here, the learning of the new classification of the new example becomes a probabilistic inference. So now we will see another classifier, which is a very famous classifier, which is called as naive Bayes classifier, and how does it work. And we will also see the advantages of naive Bayes algorithm. So in naive Bayes classifier, the Bayesian approach to classifying the new instance is to assign the most probable target value VMAP given the attribute values A1, A2 till AN. So most probable target value, which is your VMAP. So we are using the maximum a posteriori value for the target. Here we are using for the target and not for the hypothesis. So it is for the target. So that describes the instance. So VMAP is equal to your argmax, Vj element of capital V set, and probability of Vj given the attributes. What is the target classification of Vj given the attributes of that example? So now this equation can be further elaborated using the Bayes theorem, and we can write it as your Vmap is equal to argmax Vj element of V, and the term is product of the attributes given the Vj value into the product of Vj divided by the probability of the attribute values, and we can again ignore the denominator term, so it becomes argmax Vj element of V, probability of the attributes given the Vj value into the probability of Vj. So now this is the Bayesian approach. So how does we convert this into a naive Bayes classifier? Till now this is the Bayesian approach of classifying a new instance. If we are given the attributes values of the example, so what will be the most probable target value? So using the Bayes theorem we have reached till the definition of Vmap. Now we have to convert this into a naive Bayes classifier. We have to classify the target, we have to find the target value based on the naive Bayes classifier theory. So in a naive Bayes classifier, what we do is we say that the attributes, the term where the probability of attributes given the target value Vj, in this the attributes a1, a2 and an, all these attributes, they are conditionally independent. So they are conditionally independent given the value of Vj. Given the observed value of Vj, they are conditionally independent. So when the a1, a2 and an, these values are conditionally independent, the term, these subterm of the term of the total term, the subterm which is probability of attributes given Vj, it becomes a product of each and every attribute given the Vj value. So if we see your P, A1, A2, An given the Vj reduces to product of individual attribute values given the Vj value. So it becomes a product of probabilities for the individual attributes. The substitute, if we substitute this term with the product of the probabilities for the individual attributes, then what we get is we get the VNB. We get naive Bayes classifier, which is your VNB, and which is equal to argmax PVJ into product of individual probability of individual attributes given the Vj value. So here VNB denotes the target value output by the naive Bayes classifier, and notice that in a naive Bayes classifier, the number of distinct PIG Vj terms that must be estimated from training data is just the number of distinct attribute values times the number of distinct target values. So the attribute values, the number of attribute values, we get the same number of product values. So what is the advantage of using naive Bayes classifier? So here we have assumed the assumption here is that the attribute values are conditionally independent given the target value. So attribute values, they are conditionally independent. They are not independent. They are conditionally independent. Why they are conditionally independent? Because given the target value, given the condition that the target value has been observed, under that condition they are independent. So they are conditionally independent. So now the advantage here is that it is often used as a simplifying assumption in cases where the attribute values are not conditionally independent. In those cases also it works surprisingly well. Even when the conditionally independent condition assumption is not true. In those cases also it works surprisingly well. So that is the advantage of using naive Bayes classifier. Now we will see an example of naive Bayes classifier. This is an illustrative example. Here we have got 14 examples, and the attribute values are your outlook, temperature, humidity, wind, and the target value is your play tennis, which is whether to play tennis on a particular day or not. Whether you are going to say yes for playing tennis on that day, or whether you are going to say no for playing tennis on that day, particular day. So we will be classifying, for example, we will be classifying our training example, which is we'll take a new example apart from the training example. Then the example which we are going to classify is outlook is equal to sunny, temperature is equal to cool, humidity is equal to high, and wind is equal to strong. So our task is to predict the target value yes or no of the target concept play tennis for this new instance. So if we use our naive Bayes classifier equation, this is argmax. Vj has got two values. The target value has got two values, yes and no. And this is the product of pvj into the product of terms of probability of attributes given the vj. So because we have got in our training example, we have got outlook, temperature, humidity, and wind, 4 attributes. So these 4 attributes, given the target value, what will be the probability of these 4 attributes, and given the target value, which can have either yes or no as a case. So for each and every this probability of attributes, we will have 2 probabilities to consider. One in the case of yes, and the other in the case of when Vj is observed as no. So when the Vj is observed as yes and when Vj is observed as no, what is the probability of outlook is equal to sunny, and what is the probability of temperature is equal to cool, and what is the probability of humidity is equal to high, and what is the probability of wind is equal to strong. So we will be requiring a total of 10 probabilities. How we will be requiring a total of 10 probabilities? Because first of all, we will be requiring the probabilities of pvj. So vj can have 2 values. So we will be, in this case, we will be requiring 2 probabilities, whether the probability of playing tennis is equal to yes, which is 9 by 14 is equal to 0.64, and probability of playing tennis is equal to no, which is 5 by 14 into 0.36. So these are the 2 probabilities. And then we have the 4 attributes. We are going to observe the values of vj, which are 2 for each case. So we have, for the 4 attribute values, we will be getting 8 probability values. So 2 values, 2 pure probability values and 8 conditional probability values. This comes out to be total of 2 plus 8 is equal to 10 probability. So we will be needing a total of 10 probability values to find the classification of our example using the naive Bayes classification. So now we can estimate the conditional probabilities. So we will take the one. We will take example of one attribute, which is your wind is equal to strong, and when probability we have to find the probability of wind is equal to strong given the target value, which can be yes or no. So if we see P wind is equal to strong, and when the probability of when the target value play tennis is equal to yes. So in this table, we can see wind is equal to strong. If we see under the column of wind, we will see where the wind is strong, and we will see those rows where the plate NS is yes. So if we see the first row wind is weak, second row wind is strong, but plate NS is no, third row wind is weak and plate NS is yes. So again, this is not our case. Fourth row wind is weak and plate NS is yes. Fifth row wind is weak, plate NS is yes. These again are not our cases. Then sixth is strong, wind is strong and plate NS is no. Sixth row is wind is strong and plate NS is yes. So this is our case. This is the first instance. Then if we see 7th, 8th, 9th, then 10th is our case where the wind is strong. 10th row, when the wind is strong and plate NS is yes. And the 11th row, wind is strong and plate NS is yes. And finally, the second last row, weak is yes. This is not our case. And the last row, wind is strong but plate NS is no. This is again not our case. So we have got a total of all the plate NS yes cases, which are 9 cases. In those 9 cases, we have got 3 cases, which are your 6th, 10th and 11th rows, where we are finding the wind to be strong as well as plate NS to be yes. So 3 cases out of the 9 positive examples, we are finding the plate NS to be yes and wind to be strong. So here we see that probability of wind is equal to strong and plate NS is equal to yes. It comes out to be 3 by 9, which comes out to be 0.33. Similarly, if we see for the target value, plate NS is equal to no. In those cases, we will see that the P wind is equal to strong again comes out to be in 3 rows. And because we have got the negative examples, total of 5 negative examples, the probability of wind is equal to strong, given that the plate NS is equal to no, is equal to 3 by 5, comes out to be 0.60. So we can see in the table also, if when your wind is strong and plate NS is no. So if we see wind is strong, plate NS is no, the second row, and then wind is strong, plate NS is no, the 6th row, and then your last row, which is wind is strong and plate NS is no. So we have got 3 cases where the wind is strong and plate NS is no. So so the probability comes out to be 3 by 5 and it is 0.60. Similarly, we can calculate the probabilities, the remaining 6 probabilities for the other attributes, where your weather is sunny and temperature is cool, and your this high is your humidity is high, and your wind is strong. So if we see, we can calculate the remaining 6 values, and then in the naive Bayes equation, if we equate these values, we will find that for the yes training examples, the classification gives out the probability to be 0.0053, and whereas for the no training examples, the probability, naive Bayes probability, comes out to be 0.0206. So because 0.0206 is higher than 0.0053, so the naive Bayes classification comes out to be finally as no. So to this new instance, based on probability estimates learned from training data, And we can further normalize the above quantities to sum to 1. We can calculate the conditional probability that the target value is known given the observed attribute values. For the current example, this probability is we are normalizing. So this is 0.0206 divided by 0.0206 plus 0.0053, which comes out to be 0.795. So this is how we are going to use the naive Bayes classification. So we started with the Bayes theorem, then we moved on to HMAP, then we moved on to HML, then we saw the Bayes optimal classifier, which is actually the Bayesian learning, and then we saw the naive Bayes classification. So this completes my topic of Bayesian learning. Thank you.